Hello everyone, welcome to another video tutorial. Let's continue solving the problems of the chapter 2 by solving the problem 18. A single phase 3 kVA 240 to 120 volts 60 Hz transformer has the following parameters. The resistance of the high voltage winding is 0.25 ohm. Resistance of the low voltage winding, the secondary side, is 0.05 ohm. The leakage reactance of the high voltage winding is 0.75 ohm, and this is the leakage inductance of the low voltage winding. So here we have these numbers, these rated values for this single phase transformer 240 volts. Here is 120 volts. Okay, the rated value of the voltage. What is the value of the turns ratio? A is equal to the voltage of the high voltage winding divided by the voltage of the secondary winding. 240 divided by 120, that is equal to 2. So this is the ratio, 2 by 1. Part A. Determine the voltage regulation when the transformer is supplying full load at 110 volts and zero point 0.9 leading power factor. Yes, the value of the load voltage is given here. The value of the load current is corresponding to the full load current, and also we know the value of the power factor. We can use one of equations that we used for calculation of the voltage regulation to calculate, right, the voltage regulation for the part A. Here in this case, I am going to use this equation. The voltage regulation in percentage is the amplitude of V1 for the full load case minus V2 prime, the rated value, that is equal to 110, right? We need to refer this to the primary side, V2 prime, divided by the same. So to solve this problem, I'm going to use the equivalent circuit referred to the high voltage side. So in the first step, we need to calculate the resistance of the equivalent model and the leakage reactance referred to the high voltage side. So this is R equivalent, X equivalent. We should write also this is for the high voltage side. Okay. So in this case, how much is the value of the R equivalent? It is equal to the resistance of the primary winding 0.25 plus the resistance of the secondary winding times a to the power 2. You know the transformation, we did it multiple times before. Yes, we are using this model, and also you remember the equations that are used to calculate these referred values, these equations for the voltage, current, the resistance, and the leakage reactance. So here we can write these equations. The resistance of the high voltage, the equivalent resistance is equal to 0.45 ohm. This calculation. So here we have this number 0.45, and the equivalent leakage reactance, this is the leakage reactance referred to the high voltage side. So it's better if I write here equivalent. Yes, that is equal to 0.75, this number, plus 0.18 times 4. That is equal to 1.47 J times 1.47. Then we can start performing the calculations to calculate the voltage regulation. So the first one is to calculate V2 prime, the rated one. The voltage of the load is 110. This is the load that we have here. This is the load ZL, and the value of the load voltage, the rated one, is 110. This is V2 rated one. How we can refer it to the primary side? We should multiply it by A, that is 2. So V2 prime rated is equal to 220. Yes, this number A times 110, that is equal to 220 volts. The value of the current, full load current for the load, is equal to this one. This is for the primary side. I1 full load. Here, as you can see, the rated power of the transformer, the apparent power is 3 kVA. The rated voltage of the secondary is 120. So how much is the rated value of the current for the secondary side? Is 3000 divided by 120. That is equal to 25. Yes, this is the rated current here, 25 amps. The rated current for the primary is equal to this one. Yes, 12.5. This is the value of the current. Here, as you can see, the rated value of the voltage of the load is 110. Is the rated current of the load equal to this one? 3000 divided by 110? That is 27.27? No, because if we consider this number, yes, the load voltage, the load current will be equal to 27.27. This current is higher than the rated one. Yes, so this is not okay, because this transformer, the secondary side of this transformer, is designed to tolerate this current, this rated value of the current, 25 amps. Yes, so we need to consider this current for our calculations, and this will be the value of the current for the full load case in the primary winding. 12.5. How much is its angle? 25.81. So, we have also this phasor diagram. If we consider this as the rated one, V2, V2 prime, the rated one, this is the current. Because the power factor is leading 0.9. How much is the angle? You know that cosine inverse of zero point 0.9 times 180 divided by pi is 25.84. This is I2 prime for the full load, that is equal to I1 for the full load. The current that we have in the primary winding, I1 for the full load case, full load condition. So we have this angle 25.8. What is the amplitude? We calculated it here, 12.5, the amplitude. So how we can calculate the V1 full load? This voltage, this is the input voltage, V1 for the full load operating condition. Yes, just you need to write a KVL here. Okay, V1 full load is V2 prime rated one plus the full load current of the primary times the equivalent impedance that we have here. We need to calculate the voltage drop. So finally, if you do math, we will have this number. This is the amplitude of the V1 for the full load, and we can calculate the voltage regulation in percentage using this equation, that is equal to minus 0.95%. Here I did the calculations for the problem 18. This is the rated volt ampere, voltage of the high voltage winding, low voltage side, the value of the resistance, leakage reactance for the high voltage side, the low voltage winding, the turns ratio. This is the equivalent resistance, the full load current, and here I wrote the KVL. I used two methods to calculate the voltage regulation. As you know, we have different methods to calculate it. So here, if I run the M file, you can see the value of the voltage regulation calculated by method 1 and method 2. These two methods are close. You know the reason. Okay. So, yes, let's check the numbers from the reference. Chapter 2, problem 18. The part A is the same number that we calculated here. Let's go for the next part, part B. If the load terminals are accidentally short-circuited, determine the currents in the high voltage and low voltage windings. So in this case, if we have this short circuit here, the value of the load voltage becomes 0. Yes, we need to solve this circuit. We have this value of the voltage here, this impedance, and here the value of the load voltage becomes 0 in the case of the short circuit fault. So how much is the value of the current? Simply, we can write this, the V1 full load divided by the equivalent impedance. Yes, for the high voltage sides. This is the value of the current for the high voltage side. If you do math, replace the numbers. Yes, here is the amplitude of the current for the high voltage side. What is the value? Is 141.7, and you can use the transformation to calculate the short circuit current for the low voltage side, 283.5. This is the case that we have these two numbers for the part B. Okay, what is important here in the part B is the amplitude of the leakage, right, reactance that we have here. As you can see, as long as we have higher and higher values for the leakage reactance, we can reduce the value of the short circuit current. Yes, so this is the point of this problem. If we have a very low internal impedance for the transformer, the value of the short circuit current will be high. So yes, when the value of the internal impedance, right, is high, the value of the short circuit current is low, but at the same time we have a low efficiency for transformer. So we need to consider a trade-off, right, when we design a transformer between limitation of the short circuit fault currents and the efficiency of the transformer. Anyway, let's go for the next problem. Problem 19. A single phase 300 kVA 100 kilovolts to 2.2 kilovolts 60 Hz transformer has the following equivalent circuit parameters referred to the high voltage side. Here we have the equivalent core resistance, the magnetizing reactance, equivalent resistance of the primary and secondary windings, and this is the equivalent reactance. So, A, determine no load current as a percentage of full load single phase load current. How we can calculate the no load current? As you know, in the no load case, the value of the current in the secondary winding is 0, and the amplitude of the current is just because of core loss that we have and the magnetizing current. So here is the case for the no load operating mode. We can consider this circuit. The value of the current in the secondary is 0. Here we have this magnetizing reactance XM. This is the equivalent core loss resistance RC, and we apply this voltage here. In this case, this current is 0. This is I2 prime. This is I2. And the value of the excitation current, let's call this excitation current in this case, is equal to this one, summation of the core, right, current and the magnetizing current IM. This is the input voltage. The value of the high voltage winding divided by the equivalent core resistance is equal to the amplitude of the IC. Yes, the amplitude of the IC is equal to, yes, V1 divided by RC according to this circuit. And the magnetizing current, the amplitude is V1 divided by XM. So here, this is the equivalent core resistance current, 0.19 amps. The magnetizing current is 0.67. What is the value of the no load current or the excitation current? Here I wrote it in the PowerPoint equal to I no load. That is excitation current is equal to 0.699, close to zero point 0.7. And how we can calculate it as a percentage? Here you can see the value of the current for the high voltage winding is the apparent power divided by 11 kilovolts. That is 27.27. This fraction. Okay. So here is the value of the current for the high voltage winding. And what is the value of the current for the low voltage side is this one. The voltage of the secondary is 2.2 kilovolts. This is the transformer turns ratio, that is equal to 5. So here we calculated the no load current for the primary side. So we divide 0.69 to 27.27. That is equal to 2.56%. So as you can see, the value of the no load current in compared with the rated one is very low. Yes, below 3%, right? 3% of the full load current is used for magnetizing the transformer and for core loss. Okay, so this is the point of this part of the problem. The percentage of the no load current is very low in compared with the rated one when we calculate this percentage considering the rated current. So in problems that you calculate this percentage high, you should check something is wrong. Okay. The next part, no load power loss. Okay, we have the value of the equivalent core resistance for the high voltage side. The voltage is 11 kilovolts, and we can calculate the no load power loss, core loss is equal to 2.1 kilowatts. Yes. And here is the value of the power factor, the next right part of the problem. No load power factor. How we can calculate the no load power factor? In this case, in this circuit, the value of the apparent power for this magnetizing branch is equal to V1 times the current of no load. Yes. And also we calculated the active power, that is the core loss. So you know that the value of the power factor here is the core loss, the active power. We have this reactive power, and this is the S for this case, S no load. Let's call it this multiplication. So the value of the power factor for the no load case is the power loss divided by this product of amplitudes or ms values. So the value of the power factor is 0.27 lagging. We have a highly reactive load in this case. That is because of this one, xm, to magnetize the transformer. So yes, the power factor of the no load current is very low because we have a highly reactive component. The next part, full load copper loss. How we can calculate full load copper loss? We can use this equation. Yes, the previous model of the transformer that we used for the high voltage side are equivalent. This is JX equivalent, the high voltage side, and this is the low voltage side. How much is the value of the current for the high voltage winding? Is this one. We calculated it here. Finally, we can calculate the full load copper loss, or equivalent for the high voltage side times this current to the power 2. If you replace the number, this is the right amount of the loss, around 2 kilowatts. So here, as you can see, rated copper loss, right, is close to the rated core loss that we have here for this transformer. The part B, if the load impedance on the low voltage side is this one, if we have this load, yes, ZL, the amplitude is 16 and 60 degrees, this load. If we have this load, determine the voltage regulation using approximate equivalent circuit. Yes, here we have the equivalent circuit, and in this case I am going to use this equation to calculate the voltage regulation. Our load is inductive, so here the sign is the plus one. Yes, we should use this equation. The value of the load current is the rated voltage divided by the amplitude of this impedance, Z load, 2.2 kilovolts divided by 16 is 137. Yes, close to the rated one that we have here for the low voltage side. And the value of the Z base, the base value of the impedance for the high voltage side is V high voltage divided by the current of the high voltage is equal to this one, 11 E3 divided by 27.27, 403, the value of the base impedance for the primary side. Then we can calculate the R equivalent and X equivalent in per units. Yes, these two numbers. You can replace what is the value of the load impedance angle is 60. So if you replace this here and calculate cosine and sine, the value of the voltage regulation will be equal to 2.18% for this problem. So you can redo the calculations and check the numbers for this problem. Let's go for the next problem, problem 20. A single phase 250 kVA 11 kilovolt to 2.2 kilovolt 60 Hz transformer has the following parameters. This is the resistance of the high voltage winding 1.3, the leakage reactance of the high voltage, resistance of the low voltage, leakage reactance, and we have the equivalent core resistance and magnetizing reactance for the low voltage side. Part A, draw the approximate equivalent circuit magnetizing branch with RCXM connected to the supply terminals referred to the high voltage side and show the parameter values. Yes. How we can calculate the values? We need to refer them to the primary side. Here is the equivalent circuit. In this case, we connect the magnetizing branch to the source connected to the supply terminals. Yes, the magnetizing branch. This is the equivalent resistance and the equivalent leakage reactance. The rated voltage turns ratio is 5 for this transformer. The core resistance, the equivalent core resistance is this one for the low voltage side times 8 to the power 2. Transformer turns ratio is 5. 8 to the power 2 is 25. So you should multiply these two numbers by 25. This is 60 kilo ohm and this is 20 kilo ohm, the magnetizing reactance. How we can calculate the R equivalent and X equivalent? Yes, this is a better name. Similar to the previous problems. This is 1.3 plus this number times a to the power 2, 25. Our equivalent is equal to 2.55 finally. And we can do the same for the leakage reactances. 4.5 x high voltage plus 25 times this one. Okay, that is equal to 8.5. Oh, this value that we have here in this equivalent circuit. This is the part A. B. Determine the no load current in amperes for the high voltage side as well as in per unit. Similar to the previous problem. What is the value of the core current equivalent core resistance? The voltage of the primary winding divided by RC, 60 kilo ohm. Consider that we shouldn't use this number, we referred quantities to the primary side. IC is equal to 0.18 amps. What is the value of the magnetizing current? Is 11 kilovolts divided by 20 kilo ohm, 0.55. Finally, this is the value of the no load current, 0.58 amps. What is the value of the no load current in per unit? We need to know the rated values for the current. Here is the rated value of the current for the high voltage and low voltage windings. Yes, you can see the numbers. If we divide this current by the rated one, we can calculate it in the per unit. 0.025 per unit. The value of the no load current. 2.5%. Yes, the value of the no load current is low. And Also, at the same time, let's check the numbers here for this problem. The part A, yes, we calculated these numbers, the parameters of the equivalent circuit. This is the per unit value of the no load current. The same numbers that we calculated it here. Part C, if the low voltage winding terminals are shorted, determine the supply voltage required to pass rated current through the shorted winding, the losses in the transformer. Yes, this is the short circuit test. If we short the secondary winding, this one, we can calculate the value of the short circuit current and so on. So here in this case, we need to short the low voltage side, the secondary side, and calculate these quantities. Here, what is the value of the Z equivalent? The amplitude is the square root of the R equivalent to the power 2 plus X equivalent to the power 2, 8.87 of amplitude of this impedance, internal impedance. The value of the short circuit voltage will be equal to this amplitude times the rated current, because here the voltage required to pass the rated current through the short winding. So we have short circuit here. We can map the rated current. The rated current for the high voltage side is IHV. If you replace the numbers, this will be the value of the short circuit voltage that we need to apply here. This is the V short circuit that we apply to have this rated current for the primary and this rated current for the secondary. The value of the V short circuit is the amplitude of the Z equivalent times this current. Okay, not too complex. Is equal to 201, this number for the part C. The next part, losses in the transformer. Yes, how much is the value of the loss? R equivalent times the current to the power 2. This is the power loss in the short circuit test. If you replace the numbers, yes, we will have this number, 1.31 kilowatts. This number, yes, this is in watt. And what is the next part? The high voltage winding of the transformer is connected to the 11 kilovolts supply, and a load. This is the value of the ZL. We have the amplitude and angle is connected to the low voltage winding. Determine the load voltage and the voltage regulation. So in this case, we can use a similar method that we used to solve this problem. We referred quantities and calculated the load voltage, or this one, right, to solve this problem. How? Here we have the load impedance. This is the case. We have this load impedance ZL. This is the circuit. If we transfer this load impedance to the primary, we will have this circuit. This is V1 that is equal to 11 kilovolts. This is the internal impedance of the transformer Z equivalent, and this is the referred load impedance ZL prime. You know that ZL prime is A2 times ZL. Yes, so we can solve this circuit and find the load voltage and calculate the voltage regulation. So here the value of the V2 prime for the no load condition is 11 kilovolts. So if we set the value of the current I2 prime equal to 0, what will be the value of the V2 prime for the no load condition? Equal to the source voltage. So this is V2 prime for the no load, 11 kilovolts. And for the full load condition, we can calculate the current, the I2 prime for the full load, or I1 for the full load. This one, let me modify this. This is I1 for the full load is equal to the source voltage. The primary is connected, right, to 11 kilovolts. This one divided by Z equivalent, this plus Z prime L, the load impedance. So if you replace the numbers, we have this. What is the value of the ZL prime? Here, as you can see in this case, we have a capacitive load, right? A capacitor. This is minus 90 degrees. This is the ZL. We need to multiply 15 by a to the power 2. So how much is that? Times 25, 375. This is the amplitude that we have here. Okay, this one. This is equal to negative J 375. So yes, if you do math, we will calculate the I1 full load equal to 30, and this is the angle. What is the value of the V2 prime for the full load? Is equal to I1 for the full load times the ZL prime, this one. This current times this impedance is the value of the V2 prime for the full load condition, that is equal to this one. So determine the load voltage. The load voltage for this operating condition is, right, 1125. Let's check the number, this number that we have here. By referring the load to the primary, solving the circuit, and calculating the voltage. Finally, we can use this equation to calculate the voltage regulation. V2 prime no load, V2 prime full load, this definition. We fix the value of the primary voltage and calculate the change in the value of the load voltage is equal to negative 2.26%. This number that we have here for problem 20. So, okay, you can redo the calculations and solve and practice this problem. Let's go for the next problem. Problem 21, part A. The transformer is connected to a supply on the low voltage side and the high voltage side is shorted. for rated current in the high voltage winding, determine A. The current in the low voltage winding, the voltage applied to the transformer, the power loss in the transformer. So, yes, we need to do calculations of a short circuit test, but considering the low voltage side. As you know, in a standard short circuit test, we short circuit the low voltage winding and perform calculations considering the high voltage side. But in this problem, we need to do the calculations for this case. This is the transformer, 11 kilovolt. This is the low voltage winding, 2.2 kilovolt. And let's calculate the value of the R equivalent and X equivalent for the low voltage side and perform the calculations for the low voltage side. So this is the voltage of the short circuit, and here we short circuit the high voltage side. So the value of the power loss that we calculate in this case must be the same as the previous case. When we short circuit the low voltage side, we shouldn't have any difference, right? Just performing the test considering the low voltage side. How we can calculate the equivalent parameters for the low voltage side? Here are equations, the resistance of the high voltage winding referred to the low voltage side is the resistance of the high voltage side divided by A to the power 2, that is equal to 1.3 divided by 25 is 0.052 ohm. This is the value of the leakage reactance of the high voltage winding referred to the low voltage side. Here is the number 0.18 ohm, and this is the R equivalent for the low voltage winding. Summation of these two parameters, the resistance of the low voltage winding plus the resistance of the high voltage winding referred to the low voltage side. The value is 0.10, the value of this resistance. And what is the value of the X equivalent? Is this one, the leakage reactance of the low voltage winding plus the leakage reactance of the high voltage winding referred to the low voltage side, that is equal to 0.34. This is the X equivalent. So we can calculate the amplitude of the Z equivalent for the low voltage side, that is equal to 0.355. And finally, what is the value of the short circuit voltage? Is the amplitude of the Z equivalent times the short circuit current. So you know that if we are going to have this high voltage current here, the value of the current for the low voltage side will be equal to its rated value. What is the rated value of the current for the low voltage side? We did the calculation here, 113.6. So here if you replace the numbers, the value of the short circuit voltage is equal to 40.3 volts. So this is the value of the short circuit voltage. And how we can calculate the power loss for the short circuit test is the R equivalent times the current of the short circuit to the power 2, right? The loss that we have for this resistance. The value of the I short circuit is equal to the rated value of the current of the low voltage winding. Okay, this one. So if you do this calculation, the value of the power loss will be equal to 1.3 kilowatt, the same as this number that we calculated for the previous case when we short circuit the low voltage winding. So here also I wrote this M file for the part A. Here we have these parameters for the transformer, the rated apparent power, the voltage, the value of the resistance, leakage reactance, and the core resistance, and so on. Here are transformations. This is the value of the R equivalent for the low voltage side, and this is the value of the X equivalent for the low voltage side. This one is the X equivalent for the high voltage side. So this is the Z equivalent for high voltage and Z equivalent for the low voltage. The rated value of the current, the voltage of the short circuit, yes, Z equivalent times the current. So let me calculate the amplitude here. And this is the value of the power loss in the short circuit test. So if I run the code here, you can check the numbers. This is in watts, so 1.3 kilowatt. That is the same as the previous one. So now let's go for the part B of the problem 21. The high voltage side of the transformer is now connected to this voltage, right, supply, and a load is connected to the low voltage side. The load is such that rated current flows through the transformer, and the supply power factor is unity. The power factor of the supply is unity determine the load impedance, the load voltage, and the voltage regulation. Yes, so here we have this case. This is the value of the voltage of the supply. This is the transformer. You can see the ratio. Turns ratio is 5. And this is the impedance of the load. Here you can see the equivalent internal impedance of the transformer, equivalent resistance and equivalent leakage reactance, right, for the high voltage side. So how we can solve the part B? Let me copy this. We can transfer the quantities, right, to the primary side. So here we will have this circuit. This is the supply voltage Vs, the high voltage current I high voltage, the resistance, the leakage reactance, and this is ZL prime. ZL prime. So what is the value of the ZL prime? You know that ZL prime is equal to A2 times ZL. So we can solve this circuit. This is Z equivalent. Yes. So because the power factor of the supply is 1, the angle of the Vs, if we consider it equal to 0, the angle of the current also will be 0. Yes, because the power factor is unity. Here is given in the problem. So in this case, what is the amplitude of the current is equal to the rated one. Yes, because we have full load current, the rated current. The rated current in the high voltage winding is 22.72. So this is the I2 prime full load or I1 full load. Yes, this is I1 for the full load condition, the rated condition. So here we can write, that I1 full load is equal to Vs, the voltage source, divided by Z equivalent plus ZL prime. This equation. So here, this is the value of the source voltage that is also equal to V2 prime no load. Yes, we need this parameter to calculate the voltage regulation. This is the V2 prime, okay? In the case that the current is 0, the I2 prime is 0, V2 prime is equal to the Vs. So this is V2 prime no load. And in the case that we have current, we need to calculate V2 prime for the full load. So this is the procedure for calculation of the ZL. Here, as you can see, we have this parameter, this fraction, Vs divided by I1 full load is equal to 102.8, and this is the value of the ZL prime. Okay, we can calculate also the value of the ZL, the actual value, using this equation. So yes, what is the value of the V2 prime for the full load condition? We should multiply the current by the impedance of the load. So V2 prime for full load is equal to ZL prime times I1 for full load condition. Here, this equation, this is the value of the voltage, right? The load voltage for the rated current. And this is the value of the ZL, the actual value, ZL prime divided by A to the power 2, 4 minus 0.34 J. Finally, we can calculate the voltage regulation using this equation. Amplitude of V2 prime no load minus amplitude of the V2 prime for the full load condition divided by the same. If you replace the numbers, we have this voltage regulation. So let's write the code. This is the rated current for the high voltage is S rated divided by the high voltage, right, value. And here is the equation to calculate ZL prime. ZL prime is equal to this voltage divided by this current minus Z equivalent for the high voltage side. So this is ZL prime. Okay, this number. Why this is not the same as this one? Okay, because I considered a wrong parameter here. We shouldn't use the rated voltage. The source voltage is given here, and we need to perform calculations for this source voltage. So here, this is the V2 for the no load, V2 prime for the no load, this number, and this is the value of the ZL prime. Yes, Now let's check. Here is the case. This case that we have. What is the value of the current for the high voltage? 22.7. Okay, here I considered this number. 22.7 is the correct one. This ratio is actually equal to 101.2. Okay, 101.2. ZL prime is 101.2 minus this. That is equal to this one, ZL prime, 98.65. So this is the value of the ZL prime. Then what is the value of the V2 prime full load? Is this one, V2 prime for the full load condition is equal to the current of the high voltage times the impedance of the load. So this is V2 prime full load. Let's check the amplitude of this variable. ABS 2250.4. So 2250.4. What is its angle? Let's check. Times 180 divided by pi minus 4.92. This angle. Finally, this is the value of the ZL. Is the value of the ZL. The actual value is ZL prime divided by a to the power 2. This is ZL. Let's check the value. 3.94 minus 0.34 I. So here this number is 98.65. This one. Because I considered a slightly different number for the full load current. This is the rated one. And finally, we can calculate the voltage regulation. This is the equation to calculate the voltage regulation is equal to V2 prime no load minus absolute value of V2 prime full load divided by the absolute value of the V2 prime full load, the amplitude. We can multiply this by 100 to have it in percentage. So this is the value of the voltage regulation, 2.2, right? Percent. So we should use this amplitude here for the calculation of the voltage regulation for this problem. Okay, so this is the correct number. Yes, just I considered a slightly different number for the I1 full load. And here is the correct calculation. You can redo the calculations and check the numbers for the problem 21. Because we know the value of the power factor, we can do these calculations. We don't have any information for the load. Okay, so let's go for the next problem. Problem 22. A single phase 25 kVA 2300 to 230 volts transformer has the following parameters: the Z equivalent for the high voltage side and the RC, the equivalent core resistance, and the magnetizing reactance for the low voltage side. The transformer is connected to a load whose power factor varies. Determine the worst case voltage regulation for full load output. By worst case, right, in this problem, we should calculate the maximum voltage regulation. You know, we discussed this here in this problem. When we have maximum voltage regulation, using this equation, the maximum voltage regulation occurs for an inductive load when the right angle of the load impedance is equal to the angle of the Z equivalent, right? Here is the actual value, the amplitude of the Z equivalent per unit times this. So in this case, we should calculate the value of the load power factor, right? That we have the maximum voltage regulation, and finally calculate the worst case voltage regulation. The worst case occurs for an inductive load. So here we have the condition. We can replace the numbers. What is the phi angle? The angle of the Z equivalent is tangent inverse of 5 divided by 4. Let's check. A tan of 5 divided by 4 times 180 divided by pi, 51.34, this number. And now let's calculate the Z equivalent in per unit. What is the value of the Z base for the high voltage winding is V high voltage to the power 2 divided by S rated. If you replace the numbers, this will be the value of the Z base for the high voltage winding is equal to 2300 to the power 2 divided by 25E3, 211.6. So we can calculate the Z equivalent in per unit. And finally, we can calculate the maximum voltage regulation. The maximum voltage regulation is equal to amplitude of the Z equivalent in per unit. Yes, this important equation that we have. So what is the amplitude of this number? Let's check. This is the Z equivalent in per unit is 4 plus 5J divided by 211.6. Absolute value of this number times 100 is 3%. Okay, this is the value of the maximum voltage regulation. Let's check it. Right, we have the solution of this problem 22, this number. Okay, the same that we calculated it here. Anyway, we can redo calculations of this problem. Let's go for the next problem. Problem 23. For the transformer in problem 22A, determine efficiency when transformer delivers full load at rated voltage and 0.8 power factor lagging. Determine the percentage loading of the transformer at which the efficiency is maximum and calculate this efficiency if the power factor is 0.85 and the load voltage is 230 volt. So the load voltage is equal to this one, equal to the rated voltage of the secondary side. Yes, 230. So to calculate the efficiency, we should calculate core loss and copper loss. The value of the core loss is equal to, here in problem 22, we have RC for the low voltage side. So here we should calculate the core loss for the low voltage side. Is voltage of the LV winding to the power 2 divided by RC, 117.55. Okay, so this is 230 to the power 2 divided by this one. 117.55 is the core loss. What is the value of the current for the high voltage winding? Is this one, 25 kVA, 25 kVA divided by the rated voltage, 10.86. The value of the current for the high voltage winding, we know the R equivalent for the high voltage winding, so we can calculate the rated value for copper loss for the full load current is equal to this one. Okay, 4 times 10.86 to the power 2. 471 watts. What is the efficiency output power divided by the input power? The output power is equal to V2I2 times cosine of theta 2. What is the value of the V2? Is equal to the rated one delivers full load at the rated voltage. Full load means full current. Yes. So this is the S rated 25 kilovolt ampere. Cosine of theta 2 is the power factor, and we have core loss and full load copper loss. The efficiency is 97.3%. Then we need to calculate the efficiency, okay, for the load fraction that we have maximum efficiency. Okay, you remember this equation? We discussed this equation before. Here in the reference, if you check this section for transformers efficiency, the maximum efficiency condition, yes, we discussed it in previous problems. This is the condition that we have the maximum efficiency, the amount of the load fraction, the square root of full load core loss divided by the full load copper loss, this one, that is equal to 0.499. So considering this load fraction, you also remember this equation. For any load fraction, we can calculate the efficiency using this equation. If you replace the numbers, the value of the efficiency will be equal to 97.8%. Okay, so we calculated the efficiency for the part B. Consider that the load voltage is equal to the rated one. The value of the core loss is the same, and just we have a load fraction X. Anyway, You can redo the calculations. Let's go for the next problem. Problem 24. A single phase 10 kVA 2400 to 240 volts 60 Hz distribution transformer has the following characteristics. Core loss at full voltage is 100 watts. Copper loss at half load is 60 watts. The copper loss is given for half load. Part A. Determine the efficiency of the transformer when it delivers full load at zero point 0.8 power factor lagging. Okay. We can use the same equations that we had for problem 23. First of all, we need to calculate the value of the copper loss for the full load. We have this ratio, this fraction. Yes, the copper loss at any current is the load fraction to the power 2 times the copper loss for the full load. For the half load, when x is equal to 0.5, the copper loss for the half load is 60. So for the full load is 60 divided by 0.5 to the power 2. 60 divided by 0.5 to the power 2, that is 240. This is the value of the copper loss for full load current. And what is the value of the efficiency when the power factor is 0.8? The rated conditions, this is the S 10 kVA times 0.8, that is the active output power divided by the active output power plus core loss plus full load copper loss, that is equal to 95.9%. Okay, so let's repeat this calculation here. This is 10,000 times 0.8 divided by 10,000 times 0.8 plus 100 plus 240 times 100. 95.9, this number. So let's check. We have the solution of this problem. Problem 24. Okay, 95.92%, this number. Part B. Determine the per unit rating at which the transformer efficiency is a maximum. Yes, like before, determine this efficiency if the load power factor is 0.9. Again, we have the maximum efficiency for this load fraction, a square root of the core loss at rated voltage divided by the full load copper loss, that is equal to 0.646. Considering this load fraction and using this equation, we can calculate the new efficiency. Here, the power factor is higher, 0.9, and we know that the load fraction that we have maximum efficiency for it doesn't depend on the value of the power factor. So here we had this point in this problem 6. We discussed this point. The load fraction for maximum efficiency does not depend on the power factor. So here for this problem, in this case, the power factor is 0.9. Okay, not important to calculate the maximum efficiency. As long as we set the load fraction equal to this number, you can replace the numbers. The maximum efficiency for this right, load, the rated one, is equal to 96.7%. This number. This is the load fraction, and this is the maximum efficiency. The next part C, determine the efficiency when the transformer, right, has the following load cycle. We have no load for 6 hours, 70% of the full load for 10 hours at zero point 0.8 power factor, 90% full load for 8 hours at zero point 0.9 power factor. In this case, right, because we have a load cycle, we should use the all day efficiency of the transformer. What is the definition of the all day efficiency? Let's check the chapter 2 efficiency. Here we have this subsection, all day, right, or energy efficiency. The transformer in a power plant usually operates near its full load capacity and is taken out of circuit when it is not required. Such transformers are called power transformers, and they are usually designed for maximum efficiency occurring near the rated output. Yes, the power transformers. What is the transformer for this problem? Distribution transformer. What is distribution transformer? A transformer connected to the utility that supplies power to your house and the locality is called a distribution transformer. Such transformers are connected to the power system 24 hours a day and operate well below the rated power output for most of the time. It is therefore desirable to design a distribution transformer for maximum efficiency occurring at average output power. A figure of merit that will be more appropriate to represent the efficiency performance of a distribution transformer is the all day or energy efficiency of the transformer. This is the definition. The all day efficiency or energy efficiency of a distribution transformer is defined as the energy output over 24 hours divided by the energy input over 24 hours. So here we have energy output and we have loss. So how we can calculate the energy output over 24 hours? We have this load cycle, okay? The load cycle, the total output energy, yes, E out is calculated using this equation. We have 6 hours no load, so we don't have energy output for this interval. 70% of the full load for 10 hours. So 70% of 10 kVA for this power factor 0.8 times 10. I want to calculate the energy in this unit, right? Kilowatt hour. So here is for this interval. For this interval, the 90% of the full load, 0.9 times 10 kVA times zero point 0.9 power factor for 8 hours. So the E out, the energy output, is 120.8, right, kilowatt hour for this load cycle. What is the value of the core loss? The transformer is connected to the grid. the power system. And for all day, we have this amount of the core loss. The value of the core loss is equal to 100. So the core loss energy is 2.4 kilowatt hour. And what is the value of the copper loss? For this interval, we don't have any load. The value of the copper loss is 0. For this interval, the load fraction is zero point 0.7 to the power 2 times 240. This is full load copper loss, this number. And we have this equation. The copper loss at any current is the load fraction to the power 2 times the copper loss for the full load current. That is equal to 117.6. The copper loss for this interval is 0.9 to the power 2 times 240. This one. So finally, we can calculate the total energy loss for the copper is this one, 117.6 times 10 hours plus this number times 8 hours. So the summation is equal to 2.7 kilowatt hour. So the total energy loss is the energy loss for the copper and the core. That is equal to 5.1 kilowatt hour. The energy input is E out plus E loss, right? This is the energy output. This is the energy loss. The summation is 125.9. Finally, we can calculate the all-day efficiency or energy efficiency. That is equal to this fraction, 95.9. Let's check the number here. Yes, this is the efficiency for the part C. We checked the definition of the all-day efficiency, energy output over 24 hours divided by the energy output plus losses, and we calculated it for this load cycle. Okay, so you can repeat the calculations for the problem 24 and check numbers. Anyway, let's continue solving the next problems in the next video.